Morning. I think that we should get started. I am Iadunis from the University of Glasgow, and I will be sharing this session entitled Side Informations, Item Structure, and Relations. So we have 4 papers, 2 papers that are research papers, and 2 papers from industry. And we will start with the first paper, which is a research paper, entitled Full Index Deep Retrieval, End-to-End and Item Structures for Cold Start and Long-Tail Item Recommendation. So I invite Zhen Gong from Shanghai Jiaotong University to give the talk.
Hello everyone, I am Zhen Gong, coming from Shanghai Jiaotong University. It is my pleasure to be here and introduce our work for index deep retrieval to you. This is the outline of my talk, and we will introduce the background of our work first. A typical retrieval model is a 2-stage model which trains based on a 2-tower model and serves by an AN framework such as H1SW. In 2-tower and AN scenario, the objectives between retrieval and AN are usually different and independent. Their objectives are not aware of each other. So there may be a gap between these objectives, and this gap is perhaps a problem for the performance of recommendation. And end-to-end retrieval models such as deep retrieval and TDM are proposed to jointly learn retrieval and index. Their objectives are optimized at the same time. The output of item to pass mapping relationship is directly got by end-to-end retrieval models. So it is called end-to-end. Take deep and their index structure is usually a path in a graph or tree. And take deep retrieval as an example. We build a matrix-like graph as an index structure. And we choose a node from each layer, then we connect them to obtain a path. This path is regarded as an index for an item. The end-to-end retrieval models directly output the index to retrieve items. They do not involve any additional AN search process to build the index. However, there are some limitations of these end-to-end retrieval models. Take deep retrieval as an example. It only based on user item interactions, and it lacks the ability of using item features. As for long-tail or cold start items, these items do not have enough interactions with users. Their recommendation performance are not good enough. Deep retrieval is totally unable to index any cold start item, and it is not sufficient to retrieve long-tail items either. But long-tail and cold start items are usually important to recommender systems, since long-tail items account for a large proportion of items in the corpus. And the cold start item recommendation helps maintain the initiative of content creators. Long-tail and cold start item recommendation is really important to the long-term prosperity of any content sharing platform. Although long-tail and cold start items lack enough interactions with users, their side information are usually available. And these site information features are perhaps helpful to solve their recommendation problem. As for item site information, we could take a movie recommendation as an example. The actors or directors are some typical site information features. Even the newly published movies have these features. The newly published movies can be regarded as some kind of cold start items. We could use this site information to recommend some newly published movies. Even though no one have watched this movie before, we can find their potential users who is interested in these movies. Consequently, we propose the full index deep retrieval model to improve the cold start and long tail item recommendation performance. Full index deep retrieval consists of a user structure and item structure. The user structure is based on user item interactions, and item structure is based on item site information. So item structure is applicable to both cold start and long tail items. So let's start with the first part, user structure. Given a user item positive interaction pair, U and I, and we can get a model parameter theta user. Let path C be a suitable index for item I. The probability of choosing path C based on the features of user U is following equation, and the probability is usually calculated by a neural network, which is shown as the picture below. Since we assume path C is a suitable index for item I, and this path is well enough, we could derive the training objective of user structure as maximizing the log likelihood of choosing path C based on user features. Well, as for item structure, we could use similar settings to make it compatible with user structure. We also calculate the probability of choosing a suitable path with a neural network. But this neural network is input with item site information features. Item structure shares index structure with user structure, and both of these structures are compatible with each other. Note that item site information could help item structure generalize to all items, including the hot items, long tail items, and some cold start items. So this advantage greatly relieves the cold start and long tail item recommendation problem. In order to make item structure generalized to cold start and long tail items better, we also apply a few tricks to do so. We conduct popularity debias by introducing a reweighting method. We multiply the objective with the receptacle of item occurrence times, and this hampers the width of items that frequently appears in training samples. So item structure will not be dominated by these items and ignore other low-frequency items, which is important for the generalization. What's more, noise reduction by setting a threshold of path size is applied by us. This noise reduction prevents introducing noisy paths to train item structure. Since some paths in the index only have a handful of items mapped to it, when we train item structure on these paths may involve some noise. It is necessary to prevent this. And after introducing user structure and item structure, we'd like to share the joint training and inference framework. Full index deep retrieval is trained by an EM algorithm. Given that the item to pass the mapping relationship pi is discrete, so it cannot be directly optimized by a gradient-based optimizer. We optimize the model parameter and mapping in turns by an EM algorithm. First, we start with initializing model parameter theta and item to pass mapping pi randomly. Then we train them in turns. At the TC epoch, in M step, we fix the index and optimize the network parameters using a normal gradient-based optimizer to maximize the training objectives such as Q user or Q item. And in M step, we update the index structure and maximize the training objectives. In practice, 3 to 5 interactions are enough to ensure the algorithm converge. So this training framework is very efficient. In detail, full index deep retrieval has 2 training stages. First, we pre-train the user structure and obtain some suitable item to pass the mapping relationship. An item structure is learned from these mapping relationships. Then we train user structure and item structure together. In each step, we combine their objectives with multitask learning loss. In M step, we combine the paths got by them. Note that based on the side information of cold start or long tail items, item structure is able to output index for this cold start or long tail items. As for the inference of FIDR, we conduct this process in an end-to-end way. The inference does not involve any AN search process, and we only use beam search to obtain the already built paths for our users. And items are mapped to these paths. Then we can get the items already mapped directly. And full index deep retrieval does not really increase the inference burden since the user structure is already enough for the item retrieval for users. And next, we will show the experiment results to you. Here are 4 research questions. Research question 1, how does the FIDR model perform compared with the original deep retrieval model and other widely used recommendation models? We will compare the overall performance of full index deep retrieval with other baselines. And research question 2, how does the full index deep retrieval model improves the recommendation performance of cold start and long tail items? And research question 3, how does the full index deep retrieval perform on the real-world large-scale sparse dataset, such as the Douyin S dataset listed in the following table? This dataset is highly sparse and maybe more suitable to the real production environment. And the final research question is to apply the tricks like popularity debias, noise reduction, and multitask learning really help full index deep retrieval. Some ablation studies are done to test the performance of these tricks. First, we conduct experiments on 2 open source datasets, moving length 1 million and quiet record. full index performs relatively well, and it mainly beats deep retrieval and many different two-tower baselines when comparing the overall performance. And when it comes to the cold start and long-tail performance, our full index deep retrieval also do well. What's more, this is the experiment results on a real-world large-scale sparse dataset, Douyin ads dataset. Douyin is a TikTok-like video sharing platform, and these training samples are collected from some ads, so it is really sparse. And the overall performance of full index deep retrieval compared with deep retrieval is really good. And comparing with two-tower models, full index deep retrieval also shows its effectiveness on cold start items. Then we conduct some ablation studies. This shows that some tricks like popularity bias, noise reduction, multitask learning really helps the performance. And lastly, as we all know, the training and the inference efficiency are important for production environment. FIDR achieves similar training and inference efficiency compared with deep retrieval, and full index deep retrieval is much faster than two-tower models since it inherits the advantage of end-to-end retrieval models that it does not require any search process to build index. Finally, in conclusion, we tackle the problem of cold start and long-tail item recommendation for end-to-end retrieval models. And we propose item structure to learn the item-to-path mapping relationship based on item side information features, which is also available to cold start and long-tail items. And we combine item structure with user structure to build a full index for all items. And we conduct extensive experiments, and we prove that the full index deep retrieval improves the overall retrieval effectiveness while maintaining nearly the same inference efficiency. And that's all. Thank you for your time and listening.
Okay. Do we have questions from the audience? So if you have a question, please come to one of the microphones in the room. There is a question online. So let me read the question for you. So if I understand correctly, your task is conventional item recommendation. Could your approach be used for sequence recommendation?
Well, our work is about retrieval, and as far as I know, sequential recommendation is rarely applied for retrieval tasks. And I think that's perhaps, but I think that's perhaps promising. We will try it in the future.
So you made your experiments and showed that for cold start users, your performance improves. What about regular users? Did you check whether the performance for such users remains sufficiently good?
The item structure will assign some paths for cold start and long-tail items. This will squeeze some index for those hot items. So the recommendation performance of hot items do well decrease minorly, but we think it is acceptable since original deep retrieval or some other end-to-end retrieval models cannot retrieve any cold start and long tail items. And this problem is more serious. So I think this minor declinement will not harm the overall performance. As we can see in the experiments of my paper, the overall recall metric increased a lot, and it is good for the overall scope.
Okay, thank you. I think that's what we have time for. So let's thank the speaker again.
Very much.